Let us start this lecture with a thought process from great saint Swami Vivekananda, who says, "Him I call a Mahatma whose heart bleeds for the poor, otherwise he is Duratma," meaning is that he is an wicked person. So, it is a very good statement, and we will always try to work for the poor people and downtrodden, so that we can elevate ourselves as a human being. Let us recall what we learned in the last lecture. In the last lecture, we basically looked at how to find out a flight trajectory in a two-dimensional plane, of course, by using a iterative procedure, and talked about also gravitational turn. And after that, we moved to find out a relationship for the burnt out distance, and we learned also it is not only dependent on the mass ratio, it is dependent also the effective velocity, and it is dependent on the gravity as well. And of course, for this derivation we have neglected the aerodynamic drag. And then we defined and also derived a relationship for coasting height, which is generally used for sounding rocket. Today we will be discussing about the space flight and its orbit. It is very important to send a satellite to the orbit, and it will move around a particular orbit. Now, we need to look at how it is really doing and what makes it to move around an orbit about a planet or the earth. Let us look at a flight path around a circular orbit. So, if you look at this is a planet, and which is having a mass m, capital M, and this is having a radius, I can call it as a basically Rp, because this is your planet and this radius is Rp, and there is a satellite, this is your satellite, and having a very small mass, and the distance between the center of this planet and center of mass of this satellite is basically r, and this r, if you look at this r minus Rp, this will be h, altitude. If you look at altitude, h will be r minus Rp, and where r is Rp is the radius of a planet, and r is the distance between center of planet and satellite. So, keep in mind that this satellite is moving with v naught. This is basically orbital with an orbital velocity v naught. And when it is there, like this satellite is basically pulled due to the gravitational force by the planet, or in our case it will be earth if a satellite is moving around the earth. And as there is a motion, the satellite is moving with some orbital velocity, so it will be experiencing a centrifugal force. We call it a pseudo centrifugal force. So, if you take a basically a free body diagram of satellite, this is your satellite, it will be acting with the force, that is a centrifugal force, that is m, because it is moving with w. W is your angular velocity. The mass of this is your mass of the satellite, small m, and it will be omega square r, and the force, gravitational force which is acting is basically F g. And by Newton's law we know, by Newton's law we know the gravitational force F g will be basically g. G is your gravitational constant, this is mass of the planet, this is your mass of planet or earth, whatever you call, I mean, like, earth is one of the planet, and then m is the mass of your satellite divided by r square. And as this free body diagram of the satellite, you can see here free body diagram, the gravitational force is equal to the pseudo centrifugal force, that is equal to m omega square r, and that then this mass of the satellite will be cancel it out, and you will get, this is omega is your angular velocity with which the satellite is moving, is nothing but your g m by r q root over. What it indicates, if you say this is basically equation 1 kind of thing, it indicates omega is inversely proportional to the root over r q. That means the r is higher, the omega will be lower, and g is your, is basically a constant, gravitational constant, which is equal to 6.67 10 power to the minus 11 Newton meter square divided by kg square. And r is of course the radius, the distance between the center of the planet to the center of the satellite. And then we can find out V naught, which is easy. V naught is basically your orbital velocity, which is nothing but by omega into r, and that is equal to g m divided by r, and this you can call it as basically equation 2. And m, of course, we know that is the mass of earth. If you say m, mass of earth in this example you can say, or it can be any of the planet, that happens to be something 5.97 10 power to 24 kg. And we can also find out the time period to revolve around this orbit, that we can get T naught is basically time period is equal to 2 pi r by V naught, and also if you look at, that is basically omega, right, 2 pi by omega, that is equal to 2 pi into r q by g m, and this equation 3. And the time period goes on increasing when this r radius increases. And interestingly, you will find that if the h, that is the altitude. In this case altitude will be, this is your h here to this here, and we call it basically altitude. And when h is equal to 35,786 kilometer, you will get T naught is 24 hours approximately, right, hours. And of course, if the r is smaller, then the time is smaller, right, it may be order of some minutes and then kind of things. So, which we will discuss little bit later on. And keep in mind that if this orbital velocity V naught is reduced, then satellite will take an elliptical path instead of a circular path. Then we need to look at about the elliptical path. So, flight around that, let us, and if you look at this is your elliptical path, and with this is a satellite is here, and this is your planet, we can call it is it should be located at one of the focal point. This is one focal point, and this elliptical path, in this case the A is your half major axis, basically major axis will be 2a, and similarly B is your half minor axis, and this distance between this center of this planet and r is basically radius, and this is r, and r is basically instantaneous radius between planet and satellite, and this radius will be changing in its magnitude and also direction. Whereas, in case of circular orbit, the radius remains constant, but it changing its direction as it moves, right. So, and as a result, this radius, when it moves, it will be scanning the space, and then it swaps out similar space or equal area of space during an equal amount of time. So, which is being shown here in this, that means this area will be same as that area kind of things. And keep in mind that this we can define basically eccentricity of ellipse will be, can be defined as basically root over a square minus b square divided by a. And keep in mind that depending on this eccentricity, the elliptical path will be defined, and when E is 0, this orbit becomes circular. And there is another thing which you should keep in mind, and this is your basically perigee, you can say, as it is closer, this space is very closer to the planet, and this is very far away, and we call it as basically apogee. And this is having a velocity v a, and this is perigee. The perigee velocity will be very higher, and this apogee. So, that if you look at, and that depends on the radius, that means this orbital velocity will be changing as it moves around this elliptical path, and it governs by a relationship. This is your orbital velocity, v naught is r is equal to v naught a, I can call as a, and r a is equal to v p r p. this is the radius of perigee, and this you can call it as basically equation 4. And we can also keep in mind that if the, because r p is very small, this distance from r to this is your r p, right, when the satellite is here. So, this small, so therefore, V p is very higher values, whereas V naught and this distance is very very high. So, therefore, V a is small. So, therefore, V p will be greater than the V a, and that implies, and by using the Kepler law, Kepler we can have a relationship for an orbital velocity, that is V naught orbital velocity is equal to V naught is equal to root over g m. This is the mass of the planet, g is your gravitational constant as I discussed earlier. So, 2 by r minus 1 by a, and this is your, basically we can call it as equation 5. And this is a very important relation for the elliptical. You can see that if r is changing per particular a, and this V naught is keeps on changing for the same gravitational constant and same mass of the planet. That means, it is dependent on the path, and of course, the direction is changing all the time as it moves. So, we will be now basically using two orbit, one is your circular orbit, other is your elliptical orbit. A question might be coming into your mind, what are the types of orbit we can use? There are various types of orbits, but we will be discussing few of them, and based on the different criteria, total 4 types of orbits we will be discussing. And let us say that this satellite is moving around a planet, or you can say this is your earth, and we need to look at what kind of orbit it is. Of course, we have already defined it is it can be either circular, it can be elliptical, but depending on its application, if it is moving around earth, we can call it as a earth reference orbits. And this earth reference orbits also can be divided into broadly 3 categories, that is low earth orbit, the medium earth orbit, and geo earth orbit. So, if you look at, basically this is your low earth orbit, and low earth orbit is, this is your h altitude. It can be low earth orbit will be around something 160 to 2000 kilometer from the earth surface, and this is being very much preferred because of fact that it is nearer to the earth. And keep in mind that although one can have satellite in the around 160 kilometer from the earth surface, but however, the stable orbit is considered to be occurring around 185 kilometers. And if the satellite will be placed beyond the 300 kilometer of altitude from the earth surface, it will not really affected by the aerodynamic drag. That means, the aerodynamic drag for the satellite being placed beyond the 300 kilometer will be very very less. And the advantages of this low earth orbit is that it requires the less amount of energy to be placed on this orbit, and it is generally being used for weather prediction and communications and other things. And it is also having advantages because of fact that it is nearer to the earth, and any space lab or the crews are there in the space lab, you can really give services, and also if there is a problem one can also manage to reach and then do some servicing of the satellites or other space vehicles. But it is having also disadvantages because of fact that it will be moving at a little higher orbital velocity, and the bandwidth also will be low, and it is having low communication latency, and so therefore, these are the problems, and the time period will be something 128 minutes at around 2000 kilometers. That means, if you go beyond that, then there is a problem. That is a time is required. So therefore, you will have to use number of satellites in tandem or will be working in series, and it must be operated more synchronously. So therefore, these are the problem, and that is why the people are interested to have a medium earth orbit, and medium of earth orbit is basically the H range is from something around 2000 kilometer, greater than kilometer, till the 35,876 786 kilometer. And this is having a orbital period which is having more, it can go from 2 to 24 hours. We know well that this geostationary earth orbit, that is basically where you can get the the period of the rotation will be around something 24 hours, which is very important. We will be discussing about the geostationary earth orbit later on. And besides this, we will be looking at some of other based on the space, and then we can get them space reference orbits. And in that category, there is a Lagrange point is a location in the space where the combined gravitational forces of two planets, for example, like your earth and the moon, is equal to the centrifugal force felt by the satellite due to its motion. And from based on that, you can have a orbit, and planetary orbits is basically being used. You know that if you take earth as a reference, that is the inner zones from the sun itself, and there will be outer regions that planetary, and you will have to take this as a reference and also find out the orbit. Generally keep in mind that earth and then Venus are in centered with the sun, but whereas Mars and then others are not really centered with the sun as a this thing, therefore, one has to take care of. Besides this, there is a, whenever we want to have a place a satellite on the orbit, then we will have to look at how to transfer the orbit. Generally, we use various kinds of this thing. One will be elliptical orbit, Hohmann orbits, and other thing to transfer a satellite from a particular thing to another orbits. So, also interplanetary orbits is being also used to go for a other planets, and beside this, the parking orbit, there will be basically it is a temporary orbit for satellite operationals checks, and particularly when the life of the satellite is being exhausted out, then we will have to push the satellite from the actual orbit toward outward, so that it will not affected by that. And keep in mind that if this orbital will be velocity will be reduced, it may go to elliptical orbit. Generally, we face the problem of the satellite being moving around the low earth orbit because of fact that the gravitational pull of the earth will be very high, and then it will be destabilize from its path. Therefore, at regular interval it has to be given the thrust or something reboosting to for getting a stable orbit. So, that problem is always with the LEO or the low earth orbits, and if you look at, we will be discussing more about these various kinds of orbits in the next lecture. Thank you very much.